Anisotropic could be defined as the quality of a substance on showing various of physical properties when measured along different directions or different molecular axes. The word anisotropic comes from the Greek words an, which means without, isos, which means equal, and tropos, which means way. Thus, anisotropic, in a simple meaning, has different properties in different directions. Isotropic gives the meaning of the quality of a substance on showing properties with the same values when measured along axes in all directions. The word isotropic is also derived from the Greek word isos, which means equal, and tropos, which means way. Thus, isotropic is material that has the same properties in all directions. There are several properties that could help in differentiate materials that possessed either the anisotropic or isotropic behavior. One of them is the obvious in terms of the direction, in which the isotropic is not depending on the direction, whereas anisotropic materials are highly dependent on it. Next, anisotropic materials could be penetrated by light. This is due to having inconsistent properties in all directions. Meanwhile, for the isotropic materials, light cannot be penetrated into the material as it has the properties that could block the light in any direction. Chemical bonding is also another point that could differentiate between both of the main terms. Isotropic materials or minerals display a consistent and uniform chemical bonding in the mineral, while anisotropic have different and inconsistent chemical bonding. Materials that have the isotropic behavior generally appear dark, and for anisotropic materials, they show a light appearance.
An isotropic material is highly formable and may take any shape. Since the properties of its microcomponents are the same in any orientation, its behavior is also highly predictable. Metals, glasses, most liquids, and polymers are examples of isotropic materials. Meanwhile, anisotropic materials are often different kinds of woods and rocks. These types of rocks are mostly laminated in structure, while woods are naturally reinforced as seen through the orientations of their fibers. Let's take a look at amorphous solids and crystalline solids. Amorphous solids is isotropic, while crystalline solids is anisotropic for their physical property measurement. This means that the physical property measurement of amorphous solids are same in all directions and vice versa for crystalline solids. Crystalline solids have definite geometric shapes, while amorphous solids has irregular shapes. The question here is, why does the physical property measurement changes for crystalline solids? How does it become anisotropic? For crystalline solids, if physical measurements are taken along the x-axis, the reading will be different with y and z-axis, but not for amorphous solids. It will have the same measurement from all axes. To give you a better insight, we use refractive index measurement at a single wavelength fixed at the x-axis for crystalline and amorphous solids. The crystalline will have a range value, for example 1.4 to 1.6, but the amorphous will range from 1.5 to 1.52 only. When the wavelength changes direction to z or y-axis, the value changes drastically for crystalline, but remain the same for amorphous solids. This is because in crystalline solids, the x, y, and z-axis have different distribution of atoms. They have different concentration of atoms. Therefore, the measurement of physical property changes depending on the direction of the measurement. Due to the random arrangement of amorphous solids, the distribution of particles would be widely different along each axis. Hence, an average value of the measurement is taken.